If you're a network professional, then you need to understand the OSI model. The Open Systems Interconnection, or OSI model, is a conceptual framework that standardizes communication between computer systems. It divides a communication system into 7 distinct layers, each with specific functions. This layered approach simplifies network design, implementation, and troubleshooting. The OSI model promotes interoperability between different vendor equipment by defining clear interfaces between layers. It's like a blueprint for network engineers, helping them understand how data flows between computers. Each layer in the model has a specific role to play in ensuring reliable communication. The layered approach also makes it easier to identify and fix problems. Understanding the OSI model is crucial for anyone working with computer networks. It provides a common language and a structured approach to network design and management. Whether you are a network administrator, a security professional, or a software developer, a solid understanding of the OSI model is essential. Before we dive into the individual layers, let's take a moment to understand why the OSI model is so important. Imagine trying to build a skyscraper without a detailed blueprint. It would be chaotic, right? The OSI model serves as that detailed blueprint for network communication. It provides a clear structure, ensuring that every component knows its role and interacts seamlessly with others. For instance, when troubleshooting network issues, knowing the OSI model helps you pinpoint exactly where the problem lies. Is it a hardware issue, a software configuration error, or something else entirely? The OSI model breaks down the complexity, making it easier to isolate and resolve issues. Now let's delve into each layer, starting with the physical layer. Physical layer, Layer 1. The physical layer, the lowest layer of the OSI model, deals with the transmission of raw bit streams over a physical medium. This layer defines electrical, mechanical, and procedural standards for the physical connection. Examples of physical layer standards include Ethernet cables, fiber optic cables, and wireless radio waves. The physical layer is responsible for transmitting bits from one device to another, without concerning itself with the meaning of these bits. This layer ensures the reliable transmission of electrical or optical signals. Repeaters and hubs are examples of devices that operate at the physical layer. The physical layer ensures that the signals are transmitted without distortion. It also defines the data rate and transmission mode. Common examples of physical layer specifications include RS-232, USB, and Bluetooth. Data link layer, Layer 2. The data link layer is responsible for node-to-node data transfer. It establishes and terminates logical links between two directly connected nodes. The data link layer handles error detection and correction, ensuring reliable data delivery. It also controls the flow of data between devices to prevent congestion. This layer divides the data stream into frames and adds header and trailer information to each frame. This information includes source and destination MAC addresses, error detection codes, and frame delimiters. Switches and bridges are examples of devices that operate at the data link layer. The data link layer ensures that frames are delivered reliably to the next node on the network. It also manages media access control, determining which device can transmit data at a given time. Ethernet and Wi-Fi are common examples of data link layer protocols. Network layer, Layer 3. The network layer is responsible for routing packets across multiple networks. It determines the optimal path for data to travel from source to destination. The network layer uses logical addresses, such as IP addresses, to identify devices on a network. routers are the primary devices operating at the network layer. This layer adds headers to packets containing source and destination IP addresses. It uses routing protocols to determine the best path for packet forwarding. The network layer also handles congestion control and quality of service, or QoS. The network layer ensures that packets are delivered to the correct destination network, even if it is across multiple hops. IP, or Internet Protocol, is the most well-known protocol at this layer. Transport layer, also known as Layer 4. The transport layer provides end-to-end communication services between applications on different hosts. It segments data from the application layer into manageable packets and reassembles them at the receiving end. Ensuring reliable data delivery is a key function here, achieved through flow control, error handling, and congestion control mechanisms. This layer not only provides a logical connection between applications running on different hosts, but also offers services such as segmentation, sequencing, and flow control. It uses port numbers to identify specific applications or services on a host. The two primary protocols at the transport layer are TCP, which stands for Transmission Control Protocol, and UDP, known as User Datagram Protocol. TCP provides reliable, connection-oriented communication, while UDP offers a connectionless best effort service. Session layer, also known as Layer 5. The session layer manages the dialogue between applications on different hosts. It establishes, coordinates, and terminates conversations between applications. This layer provides services such as authentication, authorization, and session checkpointing. It allows applications to establish, manage, and terminate connections. Additionally, it provides synchronization services, ensuring that both sides of the communication are in sync, and also handles session recovery in case of failures. The session layer ensures that communication between applications is synchronized and orderly, providing a way to manage the exchange of data and control the flow of information. Presentation layer, also known as Layer 6. The presentation layer handles the formatting and representation of data exchanged between applications. It ensures that data from the application layer of one system is readable by the application layer of another system. This layer performs functions like data encryption, decryption, compression, and code conversion. Responsible for data translation, encryption, and compression, it converts data from the application layer into a format that can be transmitted over the network. The presentation layer ensures interoperability between systems with different data representations. It ensures that data is presented in a way that the receiving application can understand, acting as a translator between different data formats, ensuring seamless communication. The application layer, also known as Layer 7. The application layer is the topmost layer of the OSI model, directly interacting with end-user applications. It provides services that directly support user applications such as email, file transfer, and web browsing. Examples of application layer protocols include HTTP, FTP, SMTP, and DNS. The application layer is what users directly interact with when using the network, providing a wide range of services that facilitate communication and data exchange between applications. Security is also a crucial aspect of the application layer, with protocols like SSL and TLS ensuring secure data transmission. Now that we've explored the OSI model in detail, let's look at some real-world applications of this model. Understanding the OSI model is crucial not just for network professionals, but for anyone involved in IT. It helps in troubleshooting network issues, designing new network architectures, and implementing security measures. For instance, if you're setting up a secure web server, knowledge of the OSI model can help you understand how SSL/TLS protocols ensure secure communication at the application layer. Similarly, if you're working on optimizing network performance, insights from the network and transport layers can be invaluable. The OSI model also aids in the seamless integration of new technologies, whether it's cloud computing, IoT devices, or advanced cybersecurity measures. The OSI model provides a framework that ensures all components work together efficiently. Understanding the OSI model can also enhance your career prospects. Many certifications and job roles in networking and IT require a solid grasp of this foundational model. Thank you for watching. See you in the next video.